Hey guys, welcome back. We are going to keep talking about acids and bases. Last week we gave you an introduction to that and you guys investigated some pHs of common household solutions with the PhET simulation. And so this time we're going to be a little bit more mathy. So we're going to dive into the calculations behind pH and what it really represents. So if you want to get your notebooks out, we're going to go ahead and take some notes. There'll be some practice problems in here. And we will go ahead and put our notes up. All right, let's get started. So the acidity of a solution is based on the concentration of hydrogen ions, and also the basicity could be talked about as the concentration of hydroxide ions. But we're going to focus on the hydrogen ions because there's actually a relationship between the two. So it's kind of convenient. It's really established because of something called equilibrium, or the self-ionization of water. But for a water solution, so for an aqueous solution, there is this relationship between hydrogen ions and hydroxide ions. So we're going to take the molarity of hydrogen ions and multiply it by the molarity of hydroxide ions in a solution. The brackets that we have around each of the ions means molarity. So if you see brackets around a chemical, then it means we're using the molarity in that spot. So if you multiply the molarity of hydrogen ions times the molarity of hydroxide ions in a water solution, it will always equal 1 times 10 to the negative 14 at regular old room temperature. So this is a relationship that allows us to go between the two. So if I know hydrogen ion concentration, I can calculate hydroxide ion concentration and vice versa. So let's practice that first. Again, here's our relationship. 1 times 10 to the negative 14 is equal to hydrogen ion times hydroxide ion concentrations. And that 1 times 10 to the negative 14, that's a really small number. So in a water solution, there's really not that many ions present. But since the product of these two concentrations is a constant, that means when one of them gets big, the other one is going to adjust and be smaller. So they're going to always maintain that balance point between them. So for example, if hydrogen ions had a concentration that was times 10 to the negative 1, so that'd be like a 0.1 molar, then the hydroxide ion concentration would be the other part of that, so 1 times 10 to the negative 13. If you remember your exponents, when we're multiplying together two numbers that have exponents, we would add their exponents to multiply those powers of 10. So negative 1 plus negative 13 will give us negative 14. So those would go together. So 1 times 10 to the negative 1 is actually kind of big relative to hydroxide. So hydrogen ions are big in this case. That means hydroxide ions are going to have to be small. If hydrogen ions were 10 to the negative 2, then hydroxide ions would be 10 to the negative 12. So as hydrogen ions got a little smaller, hydroxide ions could get a little bigger because we'll multiply them together to get the same thing all the time. So let's practice using this formula and calculating concentrations. So here's our relationship. 1 times 10 to the negative 14 is equal to hydrogen ion times hydroxide ion concentrations. We just reshuffle this to solve for whatever we're looking for. So in the first example here, I have hydrogen ions. I want to find hydroxide. So I'm going to use this for shuffling. In my calculator, I'm going to take 1 times 10 to the negative 14, and I'm going to divide it by whatever the hydrogen ion concentration is, and that's going to give me the hydroxide ion concentrations. So again, if you know your exponents, you might be able to do this in your head. Otherwise, you're welcome to put it in the calculator. We'll be using calculators later on. Remember that when you're multiplying and especially dividing by scientific notation numbers, you want to make sure you put parentheses around your scientific notation in the calculator. So go ahead and give this a try. We've got one set up here where we know hydrogen ion, you're going to solve for hydroxide. And then the other one here, we're giving you hydroxides. We're going to use this one over here, and you're going to solve for hydrogen. So go ahead and throw those in your calculator, get a number for that, pause the video, and then we'll check our answers and see how we do. All right, let's see how we did here. So we're going to look at our first one. We've got hydrogen ion is 1 times 10 to the negative third. We're going to plug that into this formula here and solve for hydroxide. And so you guys should have gotten 1 times 10 to the negative 11th. Notice the negative 3 and negative 11 would add to be negative 14. That only works because the numbers in front are 1. When the numbers in front aren't 1, like down here, you're really better off throwing it in your calculator. So let's try that on the second one. Hopefully you guys put that in your calculator. We're actually using the second version over here. We isolated the hydrogen ion to solve for it. And then you should have gotten 3.8 times 10 to the negative 10th for this one. As far as sig figs go, I would just kind of maintain the number of decimal places that you have for the other one. So since I had 1 decimal place here, let's just get 1 decimal place there. All right, so we can use these two reshufflings of that relationship to solve for one ion concentration when we're given the other. So question for you guys, what would be the concentration if these two were equal? So if hydrogen ion and hydroxide ion concentration were equal to each other, what would that number be if they multiply together to be 1 times 10 to the negative 14? So go ahead and take a moment, calculate that, or think it through. You might be able to think it through in your head. Feel free to pause the video if you want to work on that. All right, so whether you use your calculator or you did it mentally, 1 times 10 to the negative 7 would be the concentration of hydrogen ion and hydroxide ion if they were the same, so that when you multiply them together, they would equal 1 times 10 to the negative 14. So hopefully that's going to seem useful later on when we start to talk about pH. So let's talk a little bit about those concentrations. We're going to use, we said we were going to focus on the hydrogen ion concentration to determine how acidic it is. And that's really what we're going to use when we start talking about pH as well. Most acidic solutions in life are actually really pretty dilute. And being dilute means they have a molarity less than 1. So if you think about the PhET that we did, where you looked at different pHs, all of those different substances, their hydrogen ion concentrations were something less than 1. So we want to get used to looking at numbers that are less than 1, things that are in scientific notation, and understanding if they're big or small, relative to each other. So I've got 2 numbers in scientific notation here. I've got 1 times 10 to the negative 2, and I've got 2.5 times 10 to the negative 4. So my question becomes, which one is the bigger number? So if you focus on the numbers in front, you might think 2.5 is bigger. But really, the value of the number is the front number and the power of 10 together. And so having a negative power of 10 actually moves the decimal place to the left and makes it a much smaller number. If we were to convert these numbers from scientific notation to standard notation, this one would look like this, 0.010. That is the same as 1.0 times 10 to the negative 2. And then this one would look like this, 0.00025, which is the same as 2.5 times 10 to the negative 4. So when we look at it this way, it's probably easier to tell that the number with the 2.5 is actually smaller than our 1.0 number because of the power of 10. So what we're really finding here is that concentrations that have smaller negative exponents actually have a higher concentration. So they will be a smaller negative exponent goes with a larger value, which is what we're seeing here. So it starts to feel a little backwards because we're looking for small negative numbers to represent something big. That negative brings that kind of backwards feel. But we'll get used to it. All right, so we could, if we go back to this, we could look at these concentrations as a way to decide how acidic or basic it is. But there's a lot of numbers there, it's scientific notation, it's kind of icky. Even scientists wish it were a little bit more simplified. So we have come up with another way to represent this concentration, to represent this number. And the way we're gonna look at it is we're gonna use something called pH. So when we use a log, math function of a log, it focuses on the power of 10. So I don't know how many of you guys have done logs in math class yet, but this is a log base 10. And so when you take the log of a number, it's going to essentially give you a value that focuses on the exponent, that focuses on how big it is. So for example, if we took the log of this number, 10 to the negative 2, so log of 10 to the negative 2 is just negative 2. Like it's really just going to give you that power. If we took the log of something that wasn't just the power of 10 by itself, but had a front number on it, it's still focused on that negative 2, but the 1.5 in the beginning kind of makes it wiggle a little bit. So it's a little bit more than just 10 to the negative 2 by itself because it's 1.5 times that. And so when we take the log of that scientific notation, it's still pretty close to negative 2, but it's actually a little closer to negative 1 because the 1.5 makes it a little bit bigger. So it's getting a little closer to being negative 1 than negative 2, and we can see that here in the result of taking the log. So again, we're going to use the log calculation because we're really focused on how big is the concentration. We're not so much hung up on the details, but we want to know the magnitude of the concentration. So we're going to use log to calculate pH. So this is our formula. pH is equal to negative log of hydrogen ion concentration. And so this is really just like what we've done down here, but you'll notice the powers of 10 for all of our dilute solutions are negative. So the result of taking a log is a negative number. Oddly enough, scientists don't like negatives either. So if we throw a negative in front, that means our pHs will all be positive if the concentrations are less than 1. So we're going to take the log of the hydrogen ion concentration. That would be a negative number. And then we put the negative in front because we just want it to be positive. So when we calculate pH of a solution that's got an acid or a base in it, we're only going to use strong acids and bases because that allows us to assume they break apart completely. So I'll do a couple of things. I might just give you hydrogen ion concentration. So you'll just plug it into the formula and hit the button and get your answer. Or I might give you an acid compound or a base compound, and we would want you to think about how it breaks apart. So if I give you a strong acid, what we're saying is it breaks apart completely. And you guys practiced this last time where you took acids and broke them apart and you took bases and broke them apart. So when we're saying it breaks it apart completely, what that means is if I said I'm going to give you a 0.0015 molar solution of HCl, we can assume all of those moles are going to break apart. So that goes to 0. And then where I didn't have ions before, now I'm going to get them all. So I get 0.0015 molar. And then I'll get the same for the chloride ion. So while we get the same concentration of hydrogen ions and chloride ions, we just don't care about the chloride. For pH, we're only focused on the H+. So we're really just going to look at that number. So having a certain concentration of a strong acid means you have that same concentration of H+, and that's what we're going to plug into our formula. So if our H+ concentration is 0.0015, we're going to plug that into our pH formula here. We'll take the log of that by hitting the button. It will give us a negative number, and we're just going to give the positive of that. So there is a way to figure out sig figs for pH, but we're just going to have you guys round everything off to 1 decimal place. So just as a matter of convention, we're just going to ask you guys to give pHs 1 decimal place all the time. So now we can look at this pH, and based on what we did last week, we can decide if it's acidic or basic, depending on the pH. So a pH of 2.8 is less than 7. That makes this acidic. That should seem reasonable. We put an acid in here. It should be acidic. So we're expecting that pH to be something less than 7. All right, we can do the same thing for bases. So if we have a base, if we go back here, if we just had a base like sodium hydroxide, it would break up into 1 sodium and 1 hydroxide, and that would be pretty straightforward. We're going to try one here that has 2 hydroxides in it. So this is calcium hydroxide. So same deal, if we started off with 0.0015 molar calcium hydroxide and we dump it into water, it's a strong base. We're expecting it to break apart completely. So if I started off without any ions, when the calcium hydroxide breaks apart, for every 1 calcium hydroxide, I get 1 calcium. So that's 0.0015 molar when it breaks apart. But notice there's 2 hydroxides here. So for every 2 hydroxides, for every 1 calcium hydroxide, I get 2 hydroxides. So this is actually doubled. So I have twice the hydroxide concentration as the calcium concentration because it's a 1-to-2 ratio. If this had been, again, something like sodium hydroxide where there's just 1 hydroxide, these would be the same. So this is a little bit of a variation using a hydroxide that has 2. But being strong is what allows us to make this calculation. All right, so our formula for pH doesn't use hydroxide ion concentration, it uses hydrogen ion concentration. But that's okay because you guys already know how to go between them. So we're going to use that relationship that we used before to go between hydroxide and hydrogen ion concentration. So we're going to plug in our hydrogen ion or hydroxide ion concentration and calculate hydrogen ion, and then that's what we're going to plug into our pH formula. So it just makes it a 2-step process when you have hydroxides instead of a 1-step process. Same thing happens here though. This is a number with an exponent that is negative, which means when we take the log of it, the answer will be negative, but we want it to be positive. That's why the minus is in front. So we get 11.5 for our pH. Again, we're rounding off to 1 decimal place just because. Here, our pH is greater than 7. That makes it basic. And again, hopefully that makes sense because we dumped the base in. It should be basic. So you want to make sure you're remembering what you've done. If you dumped in a base, but then you ended up with a pH less than 7, something probably went wrong. So those are our examples. Hopefully those will make sense. You guys have a practice sheet that you can look at and work through. There we are. So there's a practice sheet on Schoology, so please do work through that, check your answers, make sure it all makes sense. It is kind of broken up step by step, so you can kind of work through the different things that we did in our notes. And then after you've finished these notes, after you've worked through the practice problems, gotten all your questions answered, then there's another quiz for the week, just like last time. So another 5 questions to answer. It is mathy. There are calculations. You are expected to type in your answer for that one. So make sure you've got all your materials in front of you. You're welcome to use your notes and all that good stuff. If you guys have any questions, feel free to contact me. You can come into my office hours or you can email me anytime. And we will see you again next time.